Hello students, welcome you all again in Fundamentals of Thermodynamics lecture series. Here is lecture number 4. Till date, we have discussed about few terms starting from system, their properties, the dimensions, classification of system, classification of properties, all that. Finally, we talked about equilibrium of a system. Okay. And there I mentioned about three types of equilibrium. There is thermal equilibrium, mechanical equilibrium, and chemical equilibrium. And I have also said that if all these three equilibrium exists in a system, then we can call the system in thermodynamic equilibrium. Today, I'll start our discussion with another new term, and that is associated with change of state. Now, for the change of state to take place, we need a system, because state can be defined for a system only, and then we must have an initial point and final point. Change means that, okay, uh, initial state means, say, various properties, pressure, temperature, volume, had some values. Because of some stimulation, some effect may be caused from outside. These properties are changing, and finally, when we withdraw that cause, it settles down to another set of values. Okay, that is final properties. Okay, and this between this initial and final point, that change takes place. For example, here is a system. Here only one property is shown, so temperature, 30 degrees Celsius. We may consider pressure as well. So pressure of this system is 2 bar. Okay, I means initial. Okay, so that is initial state is clearly defined. Okay, okay, we are considering only pressure and temperature. You may consider other values, other properties. No matter. Okay, you have to consider the relevant properties. Okay, so here we are considering temperature and pressure. Say, for example. Okay, so initial state is defined of this system. Now, because of some stimulation, okay, so it may be heating. Okay, consider heating. We are heating it. Okay, that is external stimulation. Okay, it is changing. Here, once again, temperature is shown only 32. Okay, so when we heat it up, definitely its temperature will go on changing, but we won't be talking about intermediate state. No, we don't. Okay, because while this change is taking place, temperature distribution throughout the system may not be unique. Okay, there may be some set of values here, another. Okay, throughout the system, different values you can observe. But when you withdraw that external stimulation, that means here is heating. When you withdraw, so definitely system will settle down to another set of values. Say here there is a final state 32. Okay, and pressure is a 4 bar. Pressure also increases, volume not changing. Okay, pressure is a 4 bar. So initial state, final state. See, state means state in equilibrium. Okay, we don't know states in between, because their system was not in equilibrium. change was taking place. But at initial point, there was no change taking place. At final point, there is still temperature throughout constant. That is different from this, but it is constant throughout, right? So initial point and final point is fixed, identified. Now let's plot it in thermodynamic state space, because we know properties are thermodynamic coordinates. Okay, so we are considering, say, instead of 3 axis, we are considering in a 2 axis in a 2D plot. For example, these 2 axes are P and T. Here is pressure axis, here is temperature. Okay. Now plot the initial point. We know that state can be represented by a point. Okay, state means state in equilibrium. When it is in equilibrium, temperature is 20 degrees Celsius. Say here is 20. Pressure is 2. Say here there is 2. So the point will be somewhere here. Say like this. Okay, that is the initial point. Say here is 20. Here is 2. That is the initial point. How can we show final point? Okay, following the graduation over here, following the graduation over the pressure axis as well. Okay, we can say the point is somewhere here. Say that is 4 and that is 32. Okay, so initial point and final point is shown in PT axis here. Okay, fine. Okay, so change of state took place for that system. Okay, this change of state will be termed as a process. Yes, a process, a thermodynamic process. Okay, the change of state means change of any properties of any system. Okay, whatever small it may be. Say 20 to 20.1 degrees Celsius. Change of state means a process takes place. So a process will be taking place in a system when change of any properties will be noticed. Okay, say temperature of this system is 20 degrees Celsius. Somehow, because of some mean, temperature changes from 20 to 20.1. That means a process takes place inside this system. Okay, so for a process to be defined, we need initial point, final point, and obviously in which system that process is occurring, that system must be clearly defined with its boundaries. Okay, fine. Now another question may be raised, that what is the way followed by the system? Means what is the path followed, okay, by the system when its state changes from I to F. When state changes from I to F, what is the path followed? Right? Say that is the source, that is the destination. Okay, there may be various paths we can follow to reach here. Question is, what is exactly which path followed by the system? Right? Now we see, if I say that is the path followed, definitely arbitrarily said, and you can readily ask, so how can you say this? Okay, it may be, this path may be like this, okay, or like this, any path like this. How can I say this is the path followed? Actually, what I'm trying to mean is, if I say this is the path followed, the question what you can raise is, how do you know that at any intermediate point, say here, temperature will be this and pressure will be this? Whenever you are mentioning a path, that means that you know everything about all intermediate points, as I am showing by the laser pointer. You know everything about intermediate points, but we don't. Do we? No. Initial point we know 20 degrees Celsius. Final point we know 32 degrees Celsius. Final pressure we know 4. Initial pressure we know 2. But what about pressure at this point? We don't know. At this point, we don't know. And since if the intermediate points are unknown, how can I say this will be the path? Because path can only be drawn. Path can be drawn only when we know the intermediate points. Actually, we don't know about the intermediate point, because while the uh, properties were changing, the condition was something like this. There was no unique value. So how can I say at an intermediate point, say here, temperature is say 29? How can I say this? Because that is that was the condition at an intermediate uh, condition, right? So definitely the path cannot be said arbitrarily. Okay, we must know about intermediate points clearly, then only path can be defined. But how can we? How can we? Because initially it was in equilibrium, finally it is also in equilibrium. But there was no equilibrium in the intermediate condition, right? Then how can I have the path? You may ask, why? Why paths are required? Paths are required to analyze this process properly. So the path should be determined. The path of the process should be neatly drawn. To do this, here we will have one experiment. What's that? Okay, I am saying experiment, but it's a kind of thought process. And what's that? Initially, its temperature is at 20 degrees Celsius, and here's the final temperature, 32 degrees Celsius. Okay, that is the initial and final point. We know. Fine. And say for the process to take place from this initial to this final condition, say we needed uh, 10 kilojoule of heat to apply. 10 kilojoule. Okay. Now, in that thought process, what I'm going to demonstrate now, I won't apply that 10 kilojoule one at once. Say I'm applying now 0.001 joule, not 10 kilojoule at once. Okay, and I will be withdrawing it like this. Okay, so supplied and withdrawn. So because of this heat supply, definitely its temperature will no longer be at 20 degrees Celsius. It will change. Though very small change will take place, but it will change, right? So wait till that change takes place, and throughout the system, that is very important, throughout the system, another temperature, another unique value of temperature we can observe. Say like this, say 20.1. Okay, see, I am not supplying 10 kilojoule so that the temperature changes from 20 to 32. I am supplying a fraction of the total amount of heat transfer, and then I wait till another set of uh, equilibrium, another set of values of properties, relevant properties, okay, appear, and I can note that. Say temperature is 20.1, say pressure is 2.1. Okay. Again, allow the system to get heated by the same very small amount of heat, like this. Again withdrawn. So because of this heat supply, again the change will take place, though very minor change, but it will take place. And if we wait, again another set of values will appear throughout the system. Means system will be in equilibrium. Okay, say that is 20.2, and like this I'll be hitting and withdrawing that heat. Okay, that means what I'm trying to say is, what I'm trying to do is, actually I am not giving a finite change to the system, to the initial value of the system, right? Like 10 kilojoule. No. Rather, I am disturbing the system by infinitesimally small stimulation, 0.00001 joule of it, not 10 kilojoule of it at once. That would be a finite amount stimulation. Okay, so the total bulk stimulation is basically divided, okay, into very small value, means infinitesimally small value, right? This way I'll reach this condition, right? This process will be termed as quasi-static process. Quasi means almost static process. Why almost static? Because if we supply that 10 kilojoule heat at once, definitely the change in properties, what is going to take place, you can observe. You can readily observe. In that case, you can say the process is not static, rather dynamic. But in this case, since we have divided the bulk heat to a very small amount, that is why for every infinitesimally small supply, every infinitesimally small stimulation, the change will take place definitely, but that change is so small. Okay, we can say the system is almost static condition. That is called quasi-static, almost static process. But what is the benefit of this kind of thought process? Definitely it's not real one, because it's a very slow process. Any process doesn't move with such slow pace, definitely. So it's a very slow process. Even then we are discussing about it. Why? Because it gives the answer to the question raised in previous slide. What is that? What about the intermediate points? We don't know anything about intermediate points because yes, the intermediate condition, the system was not in equilibrium. Now it is in equilibrium condition. At every point it is equilibrium. And what is the benefit of system in equilibrium condition? Yes, we can have properties uniquely defined at every intermediate point. And since we know information about every intermediate points, we can plot them readily in thermodynamic axis, means thermodynamic state space, like this. Okay, so initial point, final points are known. Not only that, intermediate points also known. Okay, immediately after I, we have 20.1. After that, 20.2. So here as well we can plot it. After I, this point, we know that is 20.1. Pressure also we know. After that, this point, say 20.2, and pressure is this. Okay, so at every intermediate point we know everything about these intermediate points. Okay, we can readily plot them like this. And once the points are observed, points are found out, okay, there is no problem in drawing the path of the process as shown here. Now I can definitely say this is the path followed by the process, and now you cannot counter that how can you say this? Okay, I have just explained why I am saying this. Because now each and every points between I and F are known to me. And that is possible because of this thought process. Okay, and that thought process is quasi-static process. So one thing you please remember, the processes what we will be studying throughout the course of thermodynamics all will be assumed as quasi-static process. They are idealized substitute of the real process. Definitely, these processes are not exactly similar to the real process, but the satisfactory substitute. Okay, that means the chance of error must be there because these processes are imaginary, idealized. So, if we calculate uh, with this imaginary process, then definitely the result obtained from this analysis will differ from the actual result, what is happening actually. But still, that error will be minimum. Okay, because when we imagine this quasi-static process, the conditions imposed actually on the real process, on the real system, all those things are considered here. Like, there is one isothermal process. Isothermal means not yet discussed. Isothermal, iso means equal, thermal means temperature. Equal temperature means temperature constant. Okay. Say for when a process taking place, temperature remains constant. When we are talking about quasi-static substitute of that, we will be considering that condition also. Temperature will be constant. Okay. So this is the path followed by the process. Here is another example, similar example of quasi-static process. Say here is a gas. Here is a gas, and its temperature P, volume V, temperature should be written at capital T, and there is some weight. Because of this weight, uh, though pressure is more than atmospheric, still it stays here and piston is not moving up. Okay, gas is pressurizing it upward, and because of weight it remains there. Okay, if we withdraw this weight, definitely piston will be moving up. Okay, withdrawing this weight, that is external stimulation. Weight is nothing but a force. So because of this force, actually piston remains here. When we withdraw this force, the moment I am withdrawing, basically I am giving a stimulation to the system. What kind of stimulation? I am withdrawing a force which is actually existing right now. Okay, the moment I withdraw, the definite piston will move up, and this movement will go on till it strikes these two stops, right? And this movement of the piston will be very fast. In real process, that should happen very fast. Okay, and definitely in this initial condition, pressure, temperature you can measure, volume you can measure because it is in equilibrium. The moment you withdraw this load, okay, piston will be moving up. You agreed, and after striking these stops, if you wait for some time, you will get another set of pressure, another set of volume, and another value of volume, another value of temperature, etc. When it comes to equilibrium again, when equilibrium will be restored to its new position of the piston. Again we will get pressure, temperature, volume, etc. So that is the initial set of values, and here will be a final set of values. But at an intermediate position of the piston, when it was moving up, you cannot have unique value of pressure, unique value of temperature, etc. Why? Because it is not in equilibrium, right? So this process is real. What will be the quasi-static substitute of this? I will withdraw the same load, W, but not at once. Rather, I'll split it in very small amounts. Say W means say 10 kg. I will withdraw first, say 0.0001 gram. Like this. That means the external stimulation will be changed, but very minute change. The cause of change will be very minor, not a finite cause. Okay? Infinite is very small. Change in the cause. Okay? So I will withdraw 0.001 grams, say, for example. Definitely, because of that withdrawal, piston will move up. But that movement is very small. Okay? As if the system is almost in static condition. So there is a quasi-static process. Very slowly piston will move up, and finally when all the weights are withdrawn, it will reach here. Okay? So that process is very slow. Okay? And the benefit of this process is, at any intermediate position, we now know about pressure, temperature, volume, etc. And since we know all those values, I can readily plot it. Okay? So the path of the process will be clearly defined. Okay? That is quasi-static substitute of the real first process. And please remember, throughout the course of thermodynamics, we will be discussing about quasi-static processes only. Rather, I should say quasi-static substitutes of the real processes. Because real processes themselves we cannot study, cannot be studied. Real processes themselves cannot be studied because we don't know about intermediate points. That is why this thought process is required, and the actual or real process should be converted to its quasi-static process. The real first process should be substituted by its quasi-static counterpart, which is very slow. Okay. So here is written for the reference. You can go through it. I've already discussed. Okay. Okay. As I was saying, various processes. We'll talk about these processes later. Some processes are mentioned here. Okay. By imposing various conditions, we can have different processes like isothermal process, isobaric process, isochoric process. What are the iso means equal, as I said. Isothermal means equal temperature, means a process taking place but temperature remains constant. Isobaric, bar is the unit of pressure. Isobaric means equal pressure process. Isochoric, core means Greek word, that is space. Okay, that means equal volume. Okay, that means volume constant process. Okay, so there are various conditions. Okay, which may be imposed. To find out the quasi-static substitute, the same imposed condition should be considered. Okay. Fine. Further discussion on various processes. Say the initial condition of the system is this, as I discussed in my previous slides. 20 degrees Celsius initial point. Because of some external effect, it changes to 32, say, right? And because of some reverse effect, reverse stimulation, say this change takes place because of heating. Now I am cooling it. Reverse stimulation. This, because of that reverse stimulation, this system goes back to this. Like this. Okay. So in this case, initial point is this, final point is also this. That is nothing but another intermediate point. Now if we plot it here, that's the initial point. Okay. And when this forward process took place, say path is like this. So this red point is basically symbolizing this. Okay. Now because of some reverse stimulation, it comes back to initial. So this very point is act like final point as well. Okay. So it's a special process where initial state and final state similar. Understood? This process is known as cyclic process. Okay, where initial state and final state same. Understood? That is a cyclic process. Though this diagram definitely not look like a cycle, a circle. Okay, so it's a cyclic process when initial and final point are similar. Okay, here is it's defined. Now we'll talk about the change in properties which may take place during a process. For example, in this thermodynamic state space, I consider P, pressure, along the ordinate, volume, it should be written as V cart along abscissa. Okay. As system, I consider a piston cylinder, where initially pressure is this P1 and the volume is this much. Okay, that is 0 point, so volume is this much. Okay, I have drawn the cylinder and the piston, and piston is also I have drawn this piston and cylinder in such a manner that this 0 position of the piston coincides with 0 point of the axis, and this position of the piston coincides with this volume. That means this volume basically represents this volume, right? And the pressure, if we can measure this, that shows this pressure. Okay, so piston is initially here, pressure I can measure, that is this much, volume is this much, and since here when piston is here, volume would be 0, since piston is here, volume is this much, that is representing the volume. Okay, this one, this is the volume. Fine. Now, so because of some external cause, the substance inside, say gas, is expanding. Expansion means volume will increase. Okay, right? Volume is increasing. Volume is increasing. Okay, from V1 to V2 here. Okay, and say following this path. Okay, how do we know this path? Having a thought process, having a quasi-static substitute of the real process. Real process is first like this, there is a real process, a fast movement of the piston causing volume change from V1 to V2. See, this plane of the piston coincides with this point. So this entire volume represents V2, this volume. Okay, that is V2. Okay. And how do you know about this path? Because of quasi-static substitute of this process. Okay. That means external effect because of which this expansion took place, okay, won't be finite in our thought process. That will be infinitesimally small. Okay. That you all know, already discussed. So this 1 to 2, that is the path of the process. And if we talk about now change in properties during this process, which properties? Here only two properties are mentioned, pressure and volume. So definitely these properties we will be talking about. So what is the change in volume? Yes, final minus initial. Change means final minus initial always. So V2 minus V1, not V1 minus V2. So V2 minus V1, that is the change. Del V, V2 minus V1. What is the change in pressure? Obviously P2 minus P1. Okay, P2 minus P1. And change in volume, V2 minus V1. Now everybody, no matter what are the paths followed by this process, if we keep initial point and final point fixed, right? No matter what are the path followed, this or this or this, what we actually considered, no matter. If we keep initial point and final point fixed, change in volume will always be V2 minus V1. Since the moment piston is here, volume is definitely this amount, this, and when piston is here, volume is definitely this much. So if initial point and final point is fixed, the change in properties doesn't depend, change in properties for the process doesn't depend on the path followed, right? That is why properties are called point function, because they depends on state points. 1 and 2 state points depends on state points, point function. Properties are called point function because they don't depend on the path followed, as I have demonstrated here. Same story for pressure. Okay, at this point pressure is P1, at this point pressure is P2. No matter what are the path followed, pressure change in pressure del P for any process between 1 and 2, always P2 minus P1. So properties which we named as thermodynamic coordinates, now it will be named as point function as well, right? And since we know del phi, mathematical del phi is equal to phi 2 minus phi 1 is equal to 1 to 2 d phi, okay, and that happens in case of exact differential. So we can say properties are exact differential. Not only that, mathematically we know that integration 1 to 2 d phi is equal to what? Phi 2 minus phi 1. And it happens only when phi is exact differential. then only it can be written. Integration 1 to 2 d phi is equal to phi 2 minus phi 1. Understood? And in case of properties, we can write in the same way. That means 1 to 2 dv, we can write v2 minus v1. Okay? That is why we can also say that properties are exact differential as well. And they are path independent. Okay? That don't depend on the path followed. Depends on the initial point and the final point only. Okay? Integration limits only. Okay? That is true for any path independent. Okay? So properties are point function and exact differential. That is said here. Mathematically, if phi is a property, 1 to d phi is equal to phi 2 minus phi 1. And that is, in that case, d phi is exact differential. Right? Fine. Now, considering the same previous example, piston has moved from 1 point to 2, volume changes from V1 to V2, piston is here. Now, because of some external effect, say, piston is going back to its initial position. Right? So, what is the process taking place now? 2 to 1, not 1 to 2, 2 to 1. Okay? So, after completing this 2 to 1, basically what we are having? A cyclic process. 1 to 2, 2 to 1. See, piston has come back to its initial position. Okay? And the initial points, initial values of properties are restored. Okay? In this case, what is the change in property? Any property you can consider. Let's talk about volume. That will be easier to understand. What will be the del V for this cyclic process? Del V. Okay. To answer to this question, you please tell me what is del V for 1 to 2, the forward process? V2 minus V1. And what is del V for the reverse process? 2 to 1. V1 minus V2. Sum them up. What will I have? 0. Definitely. From this demonstration, simple animation, I can say this. When piston moves from this point to this and comes back again here in this position, del V obviously is 0. So, change in property in case of cyclic process is 0. You see, the 2 point comes back here. Right? This is a cyclic process. So, basically, if we ignore this intermediate point, now V2 minus V1 is 0. Okay, that is I is one intermediate, I represents one intermediate point. Okay, so cyclic integral of d phi is del phi cycle, that is 0. Okay, that is cyclic integral. Okay, that is that will be used in case of a cyclic process. So cyclic integral of any property is 0. Clear? So some important conclusion we have drawn. Number 1, properties are point function. Properties are thermodynamic coordinates. We have already known it. Properties are exact differential, and cyclic integral of property is 0. That's all for today. Thank you.